Hi guys, this is Maysie Calzone and this is Maysie's Algebra Initiative. In this video, we're going to go over the Unit 8 topics for Algebra 1. This includes rational versus irrational numbers, simplifying radicals, operations with radicals, and radical functions. Let's get to it. First up, we have rational versus irrational numbers. Rational numbers are a number that has either no decimals, a terminating decimal, or a repeating decimal. And my examples include 1/4, which is a terminating decimal, because if you divide 1 by 4, you get 0.25, that ends. Terminating decimal just means it ends. 1, which has no decimals. -2, which is an integer that has no decimals. 1/3 is a repeating decimal, because it's 0.33333, and that's what this line here indicates. Above the 3, that means that just repeats forever. So that makes it rational. Irrational numbers are numbers that have never-ending decimals, such as pi, which we all know the first couple letters of pi, numbers of pi are 3.14, and it goes on forever and ever with no pattern. And another example would be a fraction such as 13/17, and that is a never-ending decimal. These are the first couple numbers of it, but it keeps going on forever in no certain pattern. Okay, here's some practice. I'm going to pause the video now. You're going to identify if each number is rational or irrational, and I'll unpause the video for the answer. So pause the video now. Okay, so here's what I got. Number 1 is rational because it's just an integer. Same with number 2. It's rational. -3/4, if I plug 3 divided by 4 in my calculator, I would get -0.75, and this is rational because it's a terminating decimal. Pi, as we all know, this is one you just have to memorize, is irrational because it's 3.14, and it goes on and on and on and on and on forever. And 1/3, if I plug 1 divided by 3 into my calculator, I'll get 0.33333 to infinity forever, and that's a repeating decimal, so it is rational. Okay, so now we're going to go over radicals. What is a radical? Well, this is a radical right here. And the radical is this red sign. And that's what a radical is. And the green X, or whatever term is underneath the radical, is the radicand. And the number on the outside of this is called the index. And if there's no number there, the index is 2. So if I had this with no number here, no number, index means index is 2. Is 2. So down here, for my examples, the square root of 2 is this, because my index is 2. That means it's, because there's no number, it's going to have an index of 2, and that means a square root. And a 3 indicates a cubed root. So I have the square root of 2 and the cubed root of y. Okay, now we're going to move on to simplifying radicals. These are just numbers that we call perfect squares. And these numbers mean when they're under a radical, a square root, so index being 2, no number on the outside, that means they always come out to a single integer number. So the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3, the square root of 16 is 4, and so on and so forth. I have all the way up to 12 listed here. These are your most common square roots. So if you just see a problem that has the square root of 4, you can simplify that down to 2. Reason being is that if I did 1 times 1, it would be 1. 2 times 2 is equal to 4. 3 times 3 is equal to 9. And 4 times 4 is equal to 16. That's the reason why if I square root them, it just is finding what two numbers multiplied together. What number multiplied by itself would equal the number under the square root. That's all the square roots are. So these are your most common. And now let's keep on going. Okay. simplifying. I like using prime factorization when I simplify my radicals. So I'll show you how that works here. I already have an example written out. I'll walk you through it. So first step is when you have this, you use prime factorization to break up the number under the radical. So the number is 12. And so I got 12, and I just choose two numbers that multiply together equal 12. So 3 and 4 multiplied together equals 12. Okay, so now I move down to these two numbers. 3 is a prime number, so this is where I stop. That's the last prime number there. But 4 can be what two numbers? 4 is not a prime number. A prime number being a number that can only be created if it's multiplied by itself or 1. It can't be created by any other number. So this can be broken down further into 2 and 2. So then I list, for my second step, I list the numbers and group off in pairs of 2 because my index is 2. The pairings have to match the index. So since I have a square root here, because there's nothing we know, that's 2, I list my numbers and I do it in pairs of 2, and the only set I have here is 2 sets of 2. And I say here, if a cube root in groups of 3, would be cube root, there would be a 3 there. A fourth root would be that, and so on and so forth. But the most common you're going to see is 3 and 2, and 2 will be written as no number here. No number will be written there when it means 2. Okay. So, I have these. Now my next step is to put one number for each pair outside the radical and everything else on the inside. So I have my pair, and I put one number per pair on the outside and everything left over in the inside. So I'm left with 2 to the square root of 3. So if, in this case, I only had one number on the outside and one number on the inside, but per se, let's say I had 1 and, I would not have 1. I would have, if I had 2 and 5 on the outside and 3 and 4, I would have to multiply these numbers. Everything multiplied on the inside and everything multiplied on the outside. And we do not need it in this problem because there's only one number in each one. Okay. Awesome. So now we're going to do this one together. Step 1 is our prime factorization. So we're going to do that. So 56. Two numbers multiplied together that equal 56. We can do 28 and 2. And 2 is a prime number, so I have to stop there, but 28 is not. I could do 14 and 2. 2 is a prime number, I have to stop. And I circle it when I get my prime numbers. I have to stop. 7 and 2. Okay, 7. 7 is a prime number, I have to stop. 2 is a prime number, I have to stop. So now I have my numbers, so I list them out and find pairs. List and find pairs. So I have 7, 2, 2, and 2. So now I find my pairs. The only pair I have in a set of 2 is one pairing of 2. Now I put pairs on outside, on outside, on outside, and everything else on the inside. So I'm going to move this up here. So I'm going to have 2, and then 7 and 2 on the inside. And now see, this is where the multiplication step comes in. So multiply outside, outside, and inside. So there's nothing to multiply by 2, so that stays. And I can multiply the rest on the inside. That would be 14. And that's all there is to it. And that's all you have to do. Okay, let's move on. We have another example, this time with a cubed root, because now our index is 3. So it's the same steps, except for now I'm going to take pairs of 3, and I'll show you that. So we're going to start with prime factorization. I'm going to write prime factorization. So I have 80. Two numbers that multiply 80. We have 8 and 10. Neither of these are prime numbers, so I can break both of them down. 8 can be 4 and 2. 2 is a prime number, so we're done. 4 can be broken down to 2 and 2, both prime numbers. 10, 5 and 2, both prime numbers. So this is where we stop. So now we list and pair. List and pair. So we have 2, 2, 2, 2, and 5. And we're looking for pairs of 3 now. So I have one pair of 3, so that would be one, this, and that's the only pairs I have. So now I'm going to write the radical. So I have my radical. I have to remember the 3 here because it's a cube root. And I'm going to bring 1, 2 to the outside. And then I'm going to have a 2 and a 5 on the inside. So now I multiply them out. Multiply the insides and the outsides. So I'm going to end up with 2. There's nothing to multiply it. 2, the cube root of 10. And that's all there is to it. Okay. Here's another example, and this time we're using variables, but the same steps apply, except for when you do this, you're going to break up each term. So I'm going to show you first with just the 16. So you just take the non-variable number, so the non-letter, and you do prime factorization on it. 8 and 2, 2 and 2, 4. Those are prime numbers that can be broken down to 2 and 2. So I'm going to have 4 2's. I'm going to write this in a different color so I can do the matching step. Match, pair, whatever you want to call it. It's 4 2's, and what's our index here? 3, yes, it's 3. So we take 3, we put one of the pairs on the outside, so write radical. So we're going to have the 1 on the outside, cube root, and the 1, 2 on the inside. That's for the 16. And now we're going to do the same thing with the letters. But we're just going to write out the letters. There's only one X, and we look for pairings with the X. Is there any pairings with the X? No, there's a single X. So the X will remain on the inside. Now let's look at the Y's. How many Y's do we have? We have 1, 2, 3, 4 Y's. I just took this number, what power it is, and I wrote them all out. And I pair them up because there's a single pair. So I can I'm going to rewrite this radical down here, up here. So far I have 2, let's write that a little neater. I have 2, the cube root of 2x. Now I can bring the one pair of y's here, so I'll have a y and the remaining y here. So I'm left with my final answer of 2y, the cube root of 2xy. You see what I did with the variables? I just listed out how many I had. I only had one x, and that means I wrote out how many x's I had, and I looked for my pairs. I looked for my matching on my pairs, and there's none. There's no sets of 3. It's just a single x, so that would just remain under the radical. And then for my y's, I wrote out my 4 y's, and I paired up a single group of 3. I brought that single y to the outside, and I kept the remaining y under the radical. Okay, now we're going to move on to operations with radicals. And here's addition. You can only add radicals if they have the same radicands. Remember, radicands are the numbers underneath the doghouse, as some people like to call it, but the radical. So in this case, I could add these two. I just add the outside numbers. If there's no number that's a 1, so 3 plus 1 is 4, I get 4 to the square root of 2, because they have the same radical. I can't just add the insides and the outsides. This is incorrect, because they do not have the same radical. 3 and 2 are not the same number. Okay, here's an example of simplifying then adding. So we're going to simplify each term. So here I did all the prime factorization, and I ignored the outside term in the beginning. I ignore it, but you have to remember to put it back in at the end. So I just focused here, and I simplified them down. And so I ended up getting the 2 to the square root of 2 from this 8, and I brought down the outside term from the original, and I multiplied it by the outside term I got from this. So I ended up with 4 to the square root of 2. And I did the same thing here. I did the prime factorization of under the radical, so I simplified each term by itself. And I brought the 3 out to the end to multiply it by the outside of whatever I got here. And I got, for the first term, this term, the 2 to the square root of 8, I got 4 to the square root of 2. For the second term, 3 to the square root of 18, I got 9 to the square root of 2. You see how simplifying each, even though initially they didn't have the same radicand, I couldn't add them, but after simplifying they did, so I can now add them. So I ended up with these two numbers, I add them together, and I get 13 to the square root of 2. Okay. Here's an example. So let's look at this. Initially, these don't have the same radical. But let's see if we can simplify it. 3, that's a prime number. That can't be simplified anymore, so we're just going to be left with the square root of 3. We bring down the outside term. 3 to the square root of 3. Let's see if we can do anything with 6. 6 divides into 2 and 3. So we have our list, 2, 3. These are both prime numbers, so we stop here. Is there any pairings? No pairings. No pairs. So we're just going to end up with 2 times 6 under 3 under here, so we're going to still end up with the square root of 6, and we're going to bring down the 4. See, these didn't simplify at all. So they didn't simplify. Cannot add them. Because even when we tried to simplify them, we realized they did not simplify. So they did not simplify. And they did not have same radicand. So we cannot add them. So this is an example of even when we try to simplify, it's not going to work out. Okay, now we're going to move on to subtraction. Same rules apply as in addition as subtraction. So you can only subtract terms with the same radicand, which are these things. See over here we have 3 to the square root of 2 minus 3 to the square root of 3 minus 2 to the square root of 3. They have the same radicand. We can just subtract the outside number. So 3 minus 2 is 1. So we have the square root of 3, because when we have a 1 we just don't write it. And over here we have 3 to the square root of 4 minus 2 to the square root of 3. They do not have the same radicand number under the radical. So we cannot just subtract both the outside and the inside. This is a common misconception, but you cannot do this. That's why there's a bunch of X's right there. Okay, here's an example. We're going to do this one out. So right now, these don't have the same underneath. They don't have the same radicand at all. So let's see if we can simplify it. Remember, we start by simplifying radicals, and we do this by ignoring the outside term and just dealing with the inside term. So 5 is a prime number, so it stays the same. We can't do anything to that. We can't simplify it any further. So we're just going to have the square root of 5, and we bring the 10 back down. And let's go to 10. 10 simplifies into 5 and 2. These are both prime numbers that can't be simplified any further. So we're just going to end up with the square root of 5 times 2, because our two numbers were 5 and 2. So still the square root of 10. This didn't simplify, and we bring down the 3. So we tried simplifying them. They didn't simplify. This is another example of numbers not being able to simplify. And we can't add them. Cannot add because they do not have the same radicand. Cannot subtract. Okay. So, multiplication. These do not follow the rules of addition or subtraction. You can multiply the outside terms by the outside terms and the inside terms by the inside terms. You do not have to have the same radicand in this one. So as you can see here, we just multiplied the outside, then we multiplied the inside. See, the outside terms were 3 and 5, so 5 times 3 is 15, then 2 and 3, 2 times 3 is 6. I leave the outside on the outside, the inside on the inside. Okay, so now we're going to multiply them, then we're going to simplify them. That's what they're going to want you to do. So our first step is to just multiply. Multiply outsides, then insides. So our outsides are 2 and 6, so 2 times 6 is going to be 12, and we have a cube root. The cube root of 2 times 4 is 8. And now we're going to simplify. So when we're simplifying, we're going to first focus on radicand, which is the term under the radical. So we have 8, and 8 can divide into 4 and 2. We're using our prime factorization. 2 is a prime number, so we stop there. 4 can go into 2 and 2. And those are both prime numbers. So our list is 2, 2, and 2. And our index here is 3, because we're working with a cube root. So we have one pair of 3. So that just leaves 1, 2 on the outside and nothing on the inside. And then we bring our outside term, then multiply outside term. So nothing was left under the radical because this is an example of a perfect cube because 2 cubed is 8. So that means if I took the cube root of 8, it's going to be 2. So I bring back the outside term times 12, and I'm going to get 24. And that's going to be my final answer. Okie dokie. Okay, here's properties of radicals. These are just simple things you might want to know that might help you to manipulate radicals to your favor. So if I had a number, I'm just representing numbers by the variables x and y here. So if I had a number over another number and they were both under a radical, I could just simply write it as each individual number under a radical divided by each other. You see how they're both under the same radical, and I can rewrite them still being divided, but each under their own radicals. Here's an example with like actual numbers. So if I had the square root of 2 over 3, I could rewrite that as the square root of 2 divided by the square root of 3. And same with kind of multiplication. If I have two numbers multiplied by each other under a square root, I could just rewrite it as each individual number under a square root multiplied. So here's an example. The square root of 6 times 2 is equal to the square root of 6 times the square root of 2. These are just properties that might be useful to know. For example, I want to simplify this radical, the square root of 1 over 4. Well, I don't know how to really do prime factorization of a fraction. So I'm going to rewrite this. So my first step is going to be use properties to rewrite radical. So I have the square root of 1/4. So I can rewrite this. Remember, we had our property that allows us to rewrite this as the square root of 1 over the square root of 4. Now, at this point, I could recognize that these are both perfect squares from way back here. Where's my perfect square page? The square root of 1 is 1 and the square root of 4 is 2. This is a good thing about memorizing perfect squares. Or, let me get back to it. I could just do my prime factorization. But one thing you do have to memorize is the square root of 1 is 1. So just, that's a 1 on top. That's one you have to memorize because the prime factorization rule doesn't work too terribly well with a 1. Just know the square root of 1 or the cube root of 1, anything, and it's just a 1 under the radical, it's going to be 1. That's just something you got to know. But if you forgot that the square root of 4 is 2, you could just easily do prime factorization on it. So our step 2 is to simplify using the steps we had in our previous problem. So prime factorization here, we have 2 and 2. Those are our prime numbers. I make my list and I pair them up. I have one pair of 2, so nothing's left under the radical and I'm just left with a single 2. So this simplifies down to 1/2. Easy enough. Okay, here's some practice. I want you to simplify these radical expressions. I'm going to pause the video, so pause the video now, and unpause the video when you're ready for the answers. Okay, I'm going to walk you through each of these in my work. So here, I looked at the addition. They have to have the same radicand. They did not start with the same radicand, but I'm going to see if I can simplify them. So after doing prime factorization, I realized I didn't write down the prime factorization. I can't simplify this any further. That just stays the same. Now I'm going to move on to the 8. So I take the radicand, and I do my prime factorization, and I end up with 2 to the square root of 2. So here's my prime factorization. Here's my list. And I end up with 2 to the square root of 2. One pair of 2 on the outside, 1, 2 on the radicand, and I bring down the outside term, and I multiply it by the outside term from this, and I end up with 4 to the square root of 2. So now I rewrote both of my terms here, 3 to the square root of 2, and my new simplified 4 to the square root of 2, and they have the same radicand. Woohoo! So I just multiply them together, and I get 7 to the square root of 2. And not multiply, add them together. 3 plus 4 is 7, so I get 7 to the square root of 2. Now let's move on to number 2, the subtraction problem. They each start with the same radicand. Woohoo! I didn't have to simplify anything. I can just subtract 5 from 3. 5 minus 3 is 2, so I'm just going to get 2 to the square root of 3. Simple enough. Now, here's the multiplication one. I multiplied them together and I get 4 to the square root of 48. But I believe I can simplify this down. So I did the prime factorization of 48, and my list was 3, 2, 2, 2, 2. So I have 2 pairs of 2 on the outside and 1 3 on the inside. So that's 4 to the square root of 3. And now I must take the outside term and multiply it. So I get 4 times 4 to the square root of 3, and that's 16 to the square root of 3. I just multiply the outside terms. Now, down here, I use my property to split this up into the square root of 9 over the square root of 4. And I could either identify that these were perfect squares. The square root of 9 is 3 and the square root of 4 is 2. Or I could have just done prime factorization. For 9, I got 2 3's. So my list is 2 3's. That's a single pair. So that's 1 3 on the outside. Nothing under the radical. So it's just a 3. And the 2, I get a pair of 2's. Which means 1, 2 on the outside and nothing under the radical. So after simplifying that down, I get 3 over 2. Okay, radical functions are functions that involve radicals on a graph. So the most common one you'll see, and probably the only one you'll work with, is the square root function. And this is how the base looks like. Y equals the square root of x, starts at the origin, 0, 0, and it just goes like this. It's basically a parabola on its side. So if you turn your head and you look at it, it looks like half a parabola with this side missing. But the reason why you can't have this side is because you can never get a negative y value. Because no matter what, I cannot take a negative square root. Like, this doesn't exist. I will never have a negative y on a radical function. At least not on its base. Like, not on its base. But if I do shifts, that's another story. But that's what we're going to talk about. Okay, so that's what it looks like, just for reference. Okay, now we're going to talk about translations on a radical graph. Actually, there's one more thing I want to point out here. You notice how if I had the square root of 1 equals 1, so if I did, this was the square root of x equals y, if I go to 1 on the x and I go to 1 on the y, that's where the point is. And the square root of 4 is equal to 2. If I go to 4 on the 1, 2, 3, 4 on the graph, and I go up to where the line meets it, it's at 2. See how that works? Okay, translations of a radical graph. There's 3 translations that can occur on a radical graph. You can either have a steepness shift, which is indicated by the term in front of the radical, like this, and that's in this equation is A. A horizontal translation, which is represented by something that is underneath the radical. So anything added to the x underneath the radical is a horizontal translation. Anything added to the x, not added directly to the x, but outside the radical, will be a vertical translation. So let's see how this terms. The A term, so the number in front, which indicates our steepness. If A is less than 1, so here A is 1/2 is 1/2, let me rewrite that. 1/2 is less than 1, then it's going to make the graph grow more slowly, or it's going to kind of hug closer to the x-axis. This is our x-axis. So you see how less steep this is? Here's our base graph, and look how how much smaller it is than this is. If the number is greater than 1, so 2 is greater than 1, then it's going to grow faster. It's going to go up faster than this. So if you compare these graphs, the base here and the 2, 1, you see how this goes higher faster, and this one's more steep, like shallow, and this one's getting more and more vertical. Okay, and if you have a negative A term, that flips it over the x-axis. So you know how I said on the base you can't go below like that? Well, if there's a negative in front of it, you can. So if you ever just see a negative in front of it, just flip whatever you got over the x-axis. So this is the original here, and if I flip it over the x-axis, I get this. So I'll erase that. See, I'm just going to always have the original written here for an indication. This is the base. So a negative A term or a negative term right outside the radical indicates it's been flipped over the x-axis being this. Okay, horizontal translations, which is the H term in that long fancy equation I showed you at the beginning. And this means it's underneath the radical. It's the one underneath the radical, underneath the radical, underneath the radical. Very important. So we have our base graph here. This is just y equals the square root of x. No translations done to it. If I have a positive h term, as if it's being added to the x, it means a shift to the left. So if I had the square root of x plus 2, I go to the left 2. And now let's look over If it's a negative h term, I'm going to the right. So x minus 2, I'm going 2 to the right. You see how they have these three graphs all have the same steepness. They're all growing at the same rate. They just start in different points. The base starts at the original. If I add a number to it, I shift to the left, whatever number that is. If I subtract a number from that x underneath the radical, I shift to the right of whatever number I'm subtracting or adding. Vertical translations. This is the k term. This is outside of the radical. So our base graph is here, just normal, typical base graph. If I have a positive k or a positive number being added to the outside, like the square root of x plus 2, not under the square root, I'm going to shift up. So I'm going to go up 1, 2. If I have a negative k value, so I'm subtracting 2, and it's not under the radical, I'm shifting down. So down 1, 2. And I just take the origin, and I just shift this entire thing down 2 spaces. That means I start at the positive 2 on this one, and I start at the negative 2 on this one. Okay. Here's some practice. Graph each function. Pause the video to work it out. Then unpause the video for the answers. Okay, pause the video now. Okay, so here's what I got. By the way, these charts at the bottom, these are just written for I plugged in different values just to make sure my graphs were correct. This is just like your input-output values from linear equations. Pretty self-explanatory. I have my x values, and if I plugged in the x to the equation, I'd end up with that y value. Then I wrote the equation in the middle, so the square root of 4 minus 3 is 1, and so on and so forth. I just wrote them down. But the main focus here is the translation. So this was our base graph here, so I just graphed out a typical y equals x. I plugged in 1, square root of 1 is 1, and then over here, the square root of 4 is 2. So when I go to the 4x value, I get a 2y value. Here, x minus 3, that indicates a shift. It's underneath the radical, so it's a horizontal shift, and it's minus 3. That indicates 3 to the right. So if I started my origin here, I just go 1, 2, 3, and then I just draw my graph like my base graph, and that's how it goes. On this one, it was a vertical translation, and it's positive because it's not inside the radical with the x, and it's positive 4, so that means I go up 4. So I go up my origin, I go 1, 1, 2, 3, 4, and I just draw my graph as it would go. Okay. Thank you so much for watching. I hope you learned something new today. My name is Maysie Calzone from Maysie's Algebra Initiative, signing off.